All right, let's jump right into this explainer. You know that beige box sitting on your desk? We interact with printers every single day, right? But honestly, we rarely stop to think about the absolute symphony of high-tech physics happening just beneath that plastic casing. So what's actually happening inside your printer right now? Well, to find out, we have to look way past the paper. We're going to dive into the invisible, glowing blueprints of color theory, fluid dynamics, and electrostatics. Because as you'll see, the simple act of putting ink to paper is actually a total masterclass in modern engineering. Here is how we're going to break this down. First, the science of color. Second, the electrostatic dance. Third, the physics of inkjet. And finally, 3D and bioprinting frontiers. Let's get to it. Section 1, the science of color. Let's start with the fundamental science of how a printer actually tricks your eyes into seeing a full spectrum of colors. Okay, so there's a huge difference between how you are viewing this explainer right now and how a printed page works. Your digital screen uses the additive RGB model, literally blasting red, green, and blue light directly into your eyes. But physical printing, it relies on the subtractive CMYK model. With printing, you start with a blank white page that reflects all light, and the overlapping ink dots actually subtract or absorb specific wavelengths of that light. Take a look at this microscopic view. When tiny dots of cyan are applied to a white page, they basically act like a microscopic filter that absorbs red light. So the only light that bounces back to your eye is a mix of blues and greens. By rapidly varying the density of cyan, magenta, yellow, and black dots, the printer creates a seamless optical illusion of a full-color image. It's not just mixing paint, it is actively managing exactly which light waves are allowed to hit your retina. Moving right along to Section 2, the electrostatic dance. Now we step into the world of laser printing, which is absolutely wild, because it relies on the exact same physics as a lightning bolt. Think about rubbing a balloon against your hair, that static shock. A laser printer uses that exact same static electricity to manipulate an invisible electric field. We usually think of static as just an annoyance, right? But inside a laser printer, it's the fundamental driving force that literally moves matter from the machine onto the page, acting like a temporary glue. Here is how this electrostatic dance actually works. A laser rapidly draws a hidden blueprint of static electricity on a photosensitive drum. It draws with invisible light, discharging specific microscopic areas. Next, positively charged toner is magnetically attracted only to those discharged spots. Finally, an even stronger electric charge yanks that toner off the drum and pulls it straight onto your paper. But wait, what actually is toner? Unlike liquid ink, toner is this incredibly fine powder made of pigment and plastic. Once the static electricity places that powder perfectly on the page, the paper goes through a fuser. This applies extreme heat and pressure to literally melt those plastic particles, embedding them directly into the paper fibers. That is exactly why laser-printed pages come out warm to the touch and why they are so smudge-proof. All right, Section 3, the physics of inkjet. What if you need microscopic precision with liquid rather than melted plastic powder? This brings us to drop-on-demand, or DoD, inkjet technology, which uses two totally different methods to move liquid. First, there's thermal DoD. This was actually discovered by accident when an engineer touched a hot soldering iron to an ink-filled syringe. It literally boils the ink using a tiny resistor, creating a vapor bubble that shoots a droplet out. But then we have piezoelectric DoD, which doesn't use heat at all. In a piezoelectric printhead, an electric pulse causes tiny ceramic crystals to rapidly vibrate and change shape. Think of them as microscopic sonic pumps. When the voltage hits, the crystal physically bends, squeezing the ink chamber and ejecting a droplet with just unbelievable accuracy. And because you aren't boiling anything, this method can print a much wider variety of fluids. To truly grasp how extreme this environment is, just look at this stroboscopic image. This was captured with a 20 nanosecond spark flash. It shows the ultra-fast dynamics of a single microscopic drop forming in midair. Inside these printheads, fluids are subjected to frequencies up to 100 kilohertz, balancing the viscosity, the surface tension, and elasticity in mere microseconds. It's a literal masterclass in physics. To put that kind of speed into perspective, some continuous inkjet systems can achieve a staggering 165,000 droplets per second. That's enough to boggle the mind. And the machine directs every single one of those microscopic droplets using a magnetic flux field to either hit the paper perfectly or get recycled back into the system. Which brings us to our final stop, Section 4, Futuristic Frontiers. How are these core principles of lasers and fluid dynamics shaping the technology of tomorrow? Well, if you replace the paper with a bed of fine powder and you swap traditional ink for a chemical binding agent, you can use the exact same inkjet principles we just talked about to build three-dimensional objects layer by microscopic layer. The print head glides over the powder, firing droplets perfectly to fuse the material, and then a new layer of powder rolls right over the top. And it's an absolute game changer. This tech has evolved way beyond printing office memos. Today, we're printing FDA-approved fast-dissolving medications, flexible electronics, super complex solid ceramics, and even woven nylon. Because those piezoelectric heads don't rely on heat, they can handle incredibly delicate materials without destroying them. Of course, it's not without its hurdles. The fluid dynamics get wildly complex when you try printing onto woven fabrics, for instance. As you can see in this microscopic scan, the surface tension, the physical fiber layout, and the capillary action completely dictate your ultimate resolution. Scientists literally have to calculate how a droplet will spread and penetrate the microscopic voids of these complex surfaces. But honestly, perhaps the most mind-blowing application here is bioprinting. Because we can control those piezoelectric crystals with such extreme precision, print heads can be carefully tuned to drop on demand living mammalian cells suspended in bioink. By precisely controlling the drop formation and velocity, we can actually print cellular tissue without destroying the viability of the cells. It really shifts your entire perspective, doesn't it? So think about it. If we can successfully print living human cells today, what on earth will we be printing tomorrow? The next time you look at that humble printer on your desk, remember, it's far more than just a computer peripheral. It's a gateway to the future, built on the invisible magic of quantum-level color manipulation, electrostatics, and microscopic fluid dynamics.